Hey everyone, today we're going to be doing Leetcode 200, number of islands, and this is a Leetcode medium. I'm going to go ahead and read out the description. So given an m times n 2D binary grid, which represents a map of ones, land, and zeros, water, so ones are land and zeros are water, return the number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. You may assume all four edges of the grid are all surrounded by water. So the main thing to realize just from the description is that land is only connected to land if it is horizontal or vertically adjacent, if it's next to each other horizontally or vertically. So while these are all part of the same island, if I were to add a 0, 0 here, this 1 would be part of a different island. And you can see that in example 2, that there are actually 3 islands. 1, 1, 1, 1 here, 1 here, and this 1, 1 here. Basically, diagonal lands are not connected. So let's go ahead and make a simple example here. So I'm going to draw out a matrix. So the core realization to make about this problem is that this matrix is a graph. And you might be thinking, how is it a graph? Well, if you think about it, it's just a graph where each of these lands and waters is a node, right? So if I were to draw little nodes, it would look like this. And they're also connected horizontally as well, right? So it's a graph. And what do we think of when we think of graphs? Well, we think of search, right? And when we think of search, well, we have BFS and DFS. Now, you might be scratching your head here and thinking, I get that maybe it's a graph so we can use search, but what are we searching for? Like, the answer of this problem is going to be the number of islands. So how do we search for the number of islands? It's not in the graph. Like, usually when you're using search, you're searching for a specific node that has your answer. And here there is no node with the number of islands. Everything is a 1 or 0, land or water. And you'd be correct. But what if I told you there's a way to reduce the problem to BFS or DFS in a pretty creative way? Well, first, let me give you this. What does every island have to have? What does it start with? And, well, an island is made up of land, right? So there's one or more. For example, this island is just 1, but this island has 5 ones, right? There's 1 or more pieces of land. Now, given any node that is land, what if we had a magical function that could find all the ones that were connected to it? So it could find that, oh, this one and this one and this one and this one are all connected to this one. What if we had some magical function that could search for all these connected ones and find them? Well, we would be able to solve the problem, right? Because we would be able to go to any one, any arbitrary one, it doesn't matter, and find out all the ones that it's connected to. Let's say like there were even ones up here. I would be able to find all these ones that anyone was connected to, and then we know that that was an island, and we could add 1 to our count of islands. And then we would go to our water nodes. So we go to all our water nodes and we'd be like, oh, these are not islands. There's no way these are islands, right? We would just not consider them. But as soon as we find a 1, we could be like, oh, let's see all the ones that are connected to this 1. And here there just happens to be this 1, right? But down here, we would know that all the ones that are connected to this one or this one, doesn't matter, they're all connected. And we would know that we have 3 islands. If it wasn't being obvious enough, this magical function is BFS or DFS, because we are searching for any node that is land, that is connected. And once we've a node that is land, and once we've done that, we've found 1 island. So if we find all the islands, then we've answered the question to our problem. How many islands do we have? So if that makes any sense to you, you might be wondering, well, how do BFS and DFS work? Well, there are way better visualizations than I can draw using this blackboard, but I'll just try to do it simply. So let's say the node we're considering is 1. Well, BFS would work through this iteration first, and then it would go find the last one that is here, right? It would go kind of in these layers, spreading outwards from the first node that we're considering. Whereas if we were to go to DFS, well, DFS would go deep first. And deep is defined by in what order we consider the nodes. But let's say, just for the purposes of this example, we're going to do up, down, left, and right. We're going to start at the first node. So if row, column, if this is 0, 0, we're going to go up. We can't go up. We're going to go down. Now that we're down, we're here. We're going to see down. Can I go up? No. Can I go down? No, because down is water. Can I go left? No. Can I go right? Yes. So I'm going to go right. And then I'm going to go up, right? Because up is our first thing we do. Then I'm going to be like, oh, can I go up? Can I go? No, I can't go down because I've already been there. And this is a concept that we should try to understand here. We don't want to go to nodes that we've already been. All right. So keep that in mind. Then I have to go left. I can't go left since I've already been there. And right. Oh, can we go right? Yes. And then right, as you see that, you can see that we can no longer go up. We can no longer go down. We can no longer go left. We can no longer go right. And all these recursive calls will return. Remember when we do DFS, we like to do recursive, okay, or DFS recursion. And eventually we'll be able to find all the ones that are connected to this one. In other words, we were able to find an island. Now, remember, we don't want to visit nodes that we've already been. So what's a good way of keeping track of nodes that we've already been? My answer would be to use a data structure called a set, specifically a visited set. So this will become very useful for us to make sure we're not repeating work, and also make sure that we're not going to end up with a infinite loop where we're just going in circles. I think I've explained the idea. Now let's go ahead and put it into code. So first we have to choose, should we do it with BFS or DFS? It's kind of arbitrary because all we're searching for is all the nodes that are land. So there doesn't seem to be a more efficient way in this example between the two, but let's just go with DFS. First things first, what do we need? Well, to iterate through this grid, because we're going to consider each node, because technically each node could be an island or it could be not an island, right? So we need to figure out for each node. So let's go ahead and figure out our boundaries here. So for R in rows and for C in range calls. And let's go ahead and set these variables. We know that the rows is going to be the length of grid and the calls is going to be the length of the first array in that grid, the number of columns, right? And like we said earlier, it helps to have a set so that we're not revisiting nodes that we already visited. Misspelled this down here. So we're at our node in the iteration. So for example, we would be here starting off, right? What do we want to do once we're here? Well, we only want to consider this node as a potential island if it is land, right? Only land can be an island. So if grid RC is equal to 1. And one thing to note that is really very frustrating about this problem is that these are strings, not numbers. So just make sure you're checking that it's equal to a string and not a number, because you will lose your mind over this when you can't realize why it is not working at all. So if it's land and what? Well, we want to consider nodes that we've already been to, right? So this brings us to the question of how do we represent nodes in our set? And I think the best way is to just use a tuple. Tuple, why? Why tuple, not an array? Well, a set can only hold immutable objects. So a tuple it is. And what would this tuple be? Well, we have a simple tuple here. We just have the row and the column of our node, right? And this represents the node fairly well because we already have the matrix. So we want to make sure that it's not in our visited set. And now we can run DFS on it. So we run DFS on it, and then we will add to our result. Our result, we should initialize as 0. And I'm just going to go over here because after this magical DFS function that we've black boxed here finishes, it's going to have found all the ones that are connected to this one. So for example, these ones, this one, these ones, right? And this one. So it's going to find all these magically. It's not magically, we know it's using search, but it's going to find all of them. And then we're going to have visited all of these. So we won't visit them again. And then we will add 1 to our count. And then we'll go look for any other potential islands that might exist, although there are none in this specific example. So that basically is it. Then we're going to return the result. Very simple, right? Little thing, we have to actually write this magic box function. And I'll show you that because I chose DFS, it's really not that hard to understand if you understand DFS. So DFS on a row and a column. First, let's consider what we need to not consider. And in this case, it's going to be, well, pretty simple. What if the row or column of this node is just out of bounds? For example, -1, -1 doesn't exist in the grid, right? So we need to make sure that we're not considering any rows or columns that are or any nodes that are out of bounds. What's next? Well, we need to consider that, well, we don't want to visit any nodes that we have already visited, right? So similar to this condition down here, right? We don't want to consider any nodes that we visited. And similar to this condition, we only want to consider nodes that are land, right? So if this node is water, let's stop searching because we're searching for nodes that are land. And what is the equivalent of stop searching? Return. So get out, get out. We don't want to do any DFS anymore on this node. So we've got all the conditions there. Now, how do we go to the adjacent nodes? How do we call DFS on these adjacent nodes? Because that's what DFS does, right? It goes depth first into all of these nodes. Well, kind of a trick. Instead of writing a bunch of recursive calls, it's pretty annoying. We can instead use a directions array. And what's going to be in this directions array? Well, it's going to be the up, down, left, and right. So let me write that a little bit more clear here. So up in this case would be -1 to the row, right? What about like right? Well, right would be 1 to the column, adding 1 to the column. What would down be? Well, down would be -1 to the column. And what would left be? Well, it would be -1 to the row. If you think of it in terms of rows and columns, it's pretty easy to think of these directions. And you'll see that now we're going to do this difference in row and difference in column in DIRs, right? So dr is going to be, for example, -1, dc could be 0 for this first example. We're going to run DFS on r plus dr and c plus dc. So we would go up and then to the left, or sorry, to the right, right? And then we would go down and then we go to the left here. That's what this DIRs array kind of does. So we don't have to write all these out. It's a little bit tedious to do that. And then once we've done that, well, we have pretty much solved the problem. One thing that is easy to miss is we have this whole visited set, but we need to add our row and we need to add our node to this visited set to make sure it's not being visited multiple times. So here we go. Going to represent our nodes in terms of these tuples. And I think we have some pretty clean code here. Let's go ahead and run it. Let's see what's wrong. I got 4 here and I got 4 here. So clearly I'm not doing something correctly. Let's see. My directions were wrong. So I'm duplicating things. So up would be, yeah, -1, 0. Right would be 0, 1. Down would be 1, 0. And then this would be left. I think this should work. Forgive my ignorance there. I screwed up the directions. So we are now passing the example cases, and if we submit, see if we pass everything, and you can see, yeah, we are passing now. So that's good. Now, let's say we wanted to do BFS instead. And BFS is actually much better done iteratively. So we've solved the problem using DFS. Let's use BFS now. So how do you write the same answer using BFS? Well, first of all, BFS is much easier using iterative than recursive. So we're going to not have this recursive call anymore, but we can use a lot of the same ingredients, and I'll show you how. So main thing is, instead of using recursion, we're going to use a queue. So we'll make a queue here, and instead of recursing through all of these directions, and instead of returning, we're going to while our queue. Okay, and let's change this to call it BFS so we don't get confused here about what type of search we're implementing. So while this queue is full, we're going to start this queue with our C. So while this queue has something in it, if this something is no good, so if this something is out of bounds, the same conditions we talked about DFS, if it's out of bounds, or if it's something we visited, or if it's water, we will continue. This is similar to the return from before, right? And if it is a good node, if it's land and we haven't been there before, we add it to our set, the same set. Now, what do? We have all our directions. So for all these directions, up, left, down, and right, what are we going to do? Well, we're going to move in these directions, and instead of calling a recursive call, we're going to add it to our queue. We're not going to make a recursive call. We're not going to add it to the recursive stack. We're going to add it to our queue. And this is how you do this. We got to make sure our RC is like that here. And just to be less confusing, I'm going to change the argument here. So now we're going to append R plus dr and then C plus DC. I just want to differentiate between the arguments roll call and the row and column we're considering for each node in the queue. And now this is a iterative solution. It should work. Plus dr DC. Let's go ahead and run it. Cannot unpack non-iterable int object. So when I was making a deck out of this tuple, it was making a tuple with just 2 elements in it instead of a tuple, instead of a queue of tuples. So now that we've done it like this, go ahead and run it, and you can see that it's accepted. And we'll go ahead and submit, and you can see that the BFS works just as well too. And the cool thing about having an iterative solution is that we don't need this in its own separate function. This is just, I guess, compartmentalization. But we could have this straight up, just copy paste this code in here, and it could work too. So that is how you do this problem. And I think it's a very good pattern to learn for other matrix problems. And remember, matrices are just graphs. These are really just graph problems. So it's really useful to know how to use this way of, or the structure of coding when it comes to running BFS and DFS on these graphs represented as matrices. Hope this video helped.